How do doors affect sound insulation? This is a good question that I got from some architects today. And let's do a little explanation about that. Here's a little formula which you can use to calculate the resulting sound reduction index. So let's say if you have 2 rooms, let's see if I can sketch some kind of even a bit 3-dimensional, something like this. 2 rooms next to each other, like so. And then you know that the wall, this one, has a reduction number of, let's say it's a wall with 52 dB reduction. And then you have a door in here as well. The purple one. And then the door has, let's say, should we say 35 dB. Okay, so this would be like we do, no, not W. We should do R2 and R1. So now we have two different surfaces in this partition between these rooms, room 1 and room 2. This could be like a hotel room and a corridor outside, or it could be your apartment with the door that you come when you come home and the stairwell outside, or it could be an office, yeah, anything, a partition wall with a door in it. And you want to know what kind of door do we need to install in this partition to achieve a certain sound class, because there are some regulations to fulfill. Like if it's a dwelling, typically you want to aim at a total of 44 dBs. And then it's a combination. If you have like this, a pretty good wall with 52 decibels of reduction, and you use a 35 dB door, then the resulting will be something in between, in the middle. Now I don't have any way to quickly calculate this. Maybe I should have perhaps I do. Let's see. Yeah, actually I have it here. We need to have some kind of measurements here. Let's say it's 2.7 ceiling height and the width is 4 meters. Let's say so 4.0 meters and 2.7. And the door is 1 meter and 2 meters high. It's not according to scale, but who cares? So let's set this one like so, and we have, I'm doing some calculations now on my computer on the other side. So I put 52 decibel wall, door 35 dB, and then we just insert that into this little equation down here. So we know, we want to know what's the resulting here. We need to know R for each what's it called? Partial surface. Let's say this is surface 1 and the door has surface 2. So in that case it would be surface 2 equals 2 times 1 equals 2 square meters, whereas the surface 1 would be the width times the height, which is 4 times 2.7. But also you have to consider that it's going to be 4.4 minus, no, not minus, 4 4 times 2.7 minus S2, because you have to reduce it with that one to get that one. I mean, the total area, S total, would be equal to S1 plus S2. So that's why I have to take away the surface of the door to get the right one here. And that would be, let's see here, length 4, 2.7. The total surface area of this one would be 10.8. And that would make 10.8, I guess, minus 2. So we would end up here with 10.8 minus 2 square meters equals 8.8 square meters. Now we have everything we need here to calculate the resulting sound reduction index. And if we put in a 35 dB door in a 52 dB wall like this, then we're going to end up with, I just punched the numbers in this formula and I get 42 dBs of total sound reduction. Now, what happens if we put another door instead? We put a 40 dB door instead here. Then, oh, it's another color. Now it's my OCD here. 40 dB door instead. And then we had on the previous one, it was 42. Now if we put a 4 dB door, we get 46. So with 35 door, we get 42, and with a 40 door, we get 46 dB. Total sound reduction between these two spaces. So what you need to remember here is that when you do stuff like this, when you're gonna calculate which kind of door you need, the surface areas are very relevant, because if you have a surface area that is, let's see if we just move to the side here a little bit. If you have a case that looks like this, you have a huge partition with a small little door in there. And the other case, you have a really small partition. So this is the door. And this is the door. These are two extreme cases, but it's just to illustrate a point. Now, if you have this case number 1 and case... Oh, damn, I'm not really used to writing on the digital whiteboard. Not yet, at least. If we have case 1, you have a huge wall, which is, let's say, 52 dB and a 40 dB door. And then in the second case here, you have the same 52 dB wall and a 40 dB door. Now you see the ratio here, the wall to door ratio. In this case, the first one, the door is a very, very small partition of the whole. So that means you're going to get a better sound reduction index in total for the composite sound reduction in case 1. Whereas in case 2, the door is like 95% of the total surface. So that means even if we have a 52 dB wall here, it's just a small part of it. So the door is going to determine to a very high degree what you get here. So we could just punch the numbers and do a little experiment here. Let's say if the ceiling height here is 5 meters and the width is 20 meters. And in the second case, we have the door is the same. The door is always 2 square meters. So we put 1.1 here and 2.2 here. So it's just a little bit larger than a 2 square meter door. So in the first case, we would end up with 20 times 5. The total sound reduction in this case would be... Oh, crap. Sorry. Our total would be 51 according to my calculations here on the side. And in this other case, our total would become, let's see, the length is 1.1 and 2.2 ceiling heights. The total, oh, not an arrow. There. It's 41 dB. You see, this is an extreme example. So in normal cases, you wouldn't end up like this. But as you can clearly see here, it's the same door and the same wall in both cases. But when you change the area, the relationship between these two, the ratio of wall to door area, in this case, the door is critical. And if you need to get up to 44 dB here, you need to install a better door. The smaller the wall partition in relationship to the door, I hope that came out right. The more it is like this in the second one, the better the door. And in the first case, where you have a huge wall and a small door in relation to the wall, you can get by with a somewhat lower performing door. And that's why it's... You can't really say it's a rule of thumb that if you have this wall, you could always put in a door that is 5 dB lower than the wall and you'll be fine. Perhaps it will work in many cases, but it's no guarantee because it's all determined by this relationship between the areas. So that's how this works. And this is just like the wall partition and the door partition. In a real building, you will also have ventilation, and you will have windows and several other transmission paths when you do a composite sound reduction index. But now we're just looking at the two most obvious ones. So I hope you learned something. If you want to install a door, the smaller the wall that you're going to mount it in, the better the door you need to buy. That's what you need to remember from this one. And in today's video, I'm not wearing any fancy dapper clothes because my son is sick and I was in dad mode all day taking care of him and working a little bit on the side when I had the chance. So there's not going to be any style tips today, but always dress appropriately to the task that you want to accomplish. That's also a good rule of thumb. See you later.